Okay, so the purpose of the test, just to tell you, test, pop quiz, big boss. So purpose is not to penalize you or make you feel bad or force you to study, okay? It's to check your understanding. And the test, when we discuss the paper, is also a form of revision, okay? So as a student, right, I guess partially most of the way test is communicated to you is, you better study, if not you're a bad person. Well, I don't really think so, but it's kind of like a checkpoint for you. Okay. So if you take it seriously, then you build good habits, because there's this thing called the forgetting curve, or the memory curve, as we would have it. Okay. So I'm going to show you how that looks like. And I want to talk a bit about how to study, especially if can let Jordan in. Isn't he in already? He never requests also. Oh, okay, sorry. I just saw. Hiya. Okay. Hello, Jordan. Nice to see you. Today we're going to talk about the test. Okay. So, like, this is the forgetting curve. Let me adjust size. All right. So when you first learn something, again, when you first learn something, when I tell you some new information, when I explain some new idea to you, you may not even like remember 100% of every single sentence that I say, right? But then there's recording. So let's say when you first learn something, it's 100%. When you learn this, don't know. Okay. And then after that, as time passes, of course, you forget. So this is normally in days. So generally, after one day, you'll forget about 20% of the things that you learn. It's normal, ma. People forget stuff. Our brain is like that. Because whenever we don't review, right, our brain will think, 哎呀，这个不重要的, it's not important. We can forget about it. What do you have for lunch yesterday? You need to think a bit, right? Because your brain knows it's not important information, it's junk file. So it deletes. So you don't want your brain to, hello, excuse brain, please don't delete this important information I need for my studies. So to tell your brain to not delete this information, you have to review. Teacher, study again. I really got time. This review normally is about 10-minute one. So when I was a student, I do that. It's called speed run. But I can afford to speed run my reviews if I really learned. You see the ED here, you see the ED, that means I already think the idea. You must think the idea. When I teach you something, you cannot just say, Miss Lee say A, then B, then A, then B, then you memorize A, then B, A, then B. You must think, and I cannot do the thinking for you. Sometimes, because I teach for a while now, I can look at the student's face and I know whether the student is zoned out or teaching or learning or, braining the thing. So this is where you big brain, okay? Please, big brain. It's big brain time. If your brain is tired because of many hours of class, then you need to on hold, and then you maybe need to spend more time. So this one normally for every main idea is about 20 to 30-minute one, including trying some question across the subject. I don't care, especially the subject that needs to think. Add maths, later you do maths, especially if you do science later, add maths, physics, chemistry, bio, all the stuff. All right. So once you think already, every 10 minutes, like you just go and flip lah. What did we learn last class? Like that one. You a few times, you help your brain a bit. 5 to 10 minutes. And then you repeat the process. You will notice that the forgetting curve gets less and less steep. So you will remember better and better each time. So as you review more and more, eventually the curve will look like this. So then you will think to yourself, wow, this teacher very geng leh. How come this teacher can remember so many things? You used the wrong adjective already. It's not remember. It's because I repeat so many times. Whenever I teach, I repeat. Whenever I explain to a student who asks me questions, I repeat. Whenever I teach again to another class, I repeat. I repeat so many times because it's my job, but also because when I was a student, I understand that if you ask me to review myself, 我自己来我很闲, because I'm the kind of person where I like to play with friends lah. Some of you will know this, right? Okay, so I will go and Do you remember what we learned last week? The pressure. What? Then my friend would say, don't remember. So I go and teach a friend, you see here, got pressure, got area, blah, blah, blah. So I get to help my friend. I get to help myself. It's big brain solution, modern solution. But if you're a type where, you know what, miss, I prefer to draw. I prefer to doodle. Okay, no? Doodle your revision, draw a flow chart. Review in a way that makes sense to you and make you feel good. You have to hack your brain, you have to help your brain a bit. Online learning very tough, no social cues. You don't get to see everything. You only get to see a small little window. Help your brain, okay? So you can see the test as a way for you to, as an incentive for you to remind a few times and then just see whether your retain knowledge, remember is there. Of course, it will still drop lah. So for example, I didn't learn bio for like 20 years already. Am I revealing my age a bit, right? Didn't learn bio for 18 years. So I don't remember a lot of stuff because I didn't use it now. Okay. So check understanding and for revision. Okay. What will we do? We have completed 2 units right at the end of unit 2. But unit 1, I will ask, okay, I'm telling you what I will ask. Tell you already what I will ask. Tell you already what to study. So unit 1, I'm going to look at kinematics. So I will set questions around displacement, velocity, acceleration. Okay, so I am going to look at the graph. So if you sudah lupa because it's long time ago, here's where you can go. Okay, go classwork. Scroll. I'm not going to ask equation or motion because it's extension. Okay, I teach you this because you learn this in your Form 4. Maybe a bit of equation. Okay, so this one. If you want a hack, look at homework law. How many people turn in? Don't know. Okay, so you can click, you can look at the work. So I'm gonna set a question regarding this kind of graphs. I'm not going to tell you what graph lah. If I tell you everything, what are you going to study? Because I haven't decided what graph I'm going to ask. Okay, so describe the motion, calculate basic thing like speed. Review a homework law, you should have done already. So you're done, you turned in. Okay, got question? Ask me. Equation of motion is not in O levels, but it is in SPM. So I teach you because we are at that region already. So I shouldn't teach you, so to open up the brain, exercise a bit, increase your range. But I've been training you. Actually, I've been training you IG plus SPM lah. Basically, I'm teaching you things that you need to know so that you can progress to A levels. Slowly, bit by bit. But for tests, I'm not going to test that long. Okay. Maybe I set a bonus section. Let me know if you want a bonus section. I'll set that. Okay. I'm going to look at graph. I'm going to look at describing based on the graph. How do you know it's accelerating, traveling faster, slowing down, stop, not moving? All that I will ask, confirm. Okay. Then I'll ask you to do some basic calculation. Make sure you know how to find gradient, and the gradient of the graph means what? For example, gradient of displacement time. What is gradient of displacement time? Go look at your notes now. I tell you, you need to go and revise. Okay, displacement time and velocity time. They represent something. One represents velocity, one represents acceleration. Why though? Go study. Okay, I think more or less like that lah. Okay, and then unit 2, I'm going to look at forces. Okay, again, you go back here and stare at your Google Classroom. Where's my Google Classroom? Okay. So the extension, whenever I type extension, no need to study yet. Okay, so I'm going to look at moment of forces. Okay, and I'll talk about vectors and Hooke's law. Maybe I'll ask the paper 6. So forces, moment, Hooke's law, vector. Okay 啦，好像没有了。That's it. Will I ask pressure? Do you want pressure? Can ask lah. I'll ask a bit. I'll ask what we do today. So this one's fresh. So I'm going to talk about solid and liquid. Gas we keep for later lah. All right, that's it. It's going to be roughly 40-ish minutes. I haven't set the format yet. I haven't thought about it yet. I will let you know later. But I'm going to need you to turn on your webcam. So if your webcam is GG, or you don't have webcam, or your data is GG, you let me know, okay? I can give you exemption, but I need to know what is going on. All right. So I'm not like you must turn on the camera, but then you have to let me know. Okay, so let's look at last week's work. I will upload this one. I'll put it inside Google Classroom. If I haven't put in and you want it now, then you message me lor. Just message me. I won't bite. I will reply. Okay, help me a bit by saying that, oh teacher, I need it now. Can, don't worry. Okay, let's look at your homework. Where? Here, this one. Okay. Show. Okay. So this one is a spring question regarding Hooke's law. So again, it's to extend backwards so that you have some kind of revision set up. State two properties of an object that may be changed by the action of forces. And if you remember when I started pressure, I reviewed all of this. Accelerate, change direction, change shape, exert pressure, all these also can. So I think the easiest one is to properties of the object. Number one, shape. Okay, number two, you can say motion or speed, because this one causes acceleration. Okay, these are the most straightforward ones. Next, a chest expander is a piece of equipment used by athletes in a gym. So it's not being used like that lah. Okay, this one is very dangerous. Like, imagine 这个人手滑wet and then the spring slip out of his hand then whack this person on the face. Wow, very painful. Okay, better not. So a chest expander, which is not always the best way to use, but we use it this way lah. Okay, look at my dude. Like that one. So the spring is here. Actually, he's not using spring, he's using rubber band or some elastic band. Oh, we use the elastic band because rubber doesn't rust, won't corrode, and it's lighter to carry around. Let's say you want to pack this in your luggage, you go traveling, then you want to work out because you need to keep the gains, keep the muscle. So you can see when he's stretching, let's say when I stretch here, he's exerting force in this direction and this direction. Okay. You know what? I'm just going to crop this, but I think you get the idea already. Of course, there are many ways to use this this device. Okay, so this is my dude. This one I don't recommend because it looks very dangerous. Person let go. You see, if let's say this hand slip, right? Although it's highly unlikely because he's hooking the hand there. But if let's say it's fixed, right? What will happen is that this one will fly away, fly outwards in this direction. It's still not that bad, right? It won't hit him in the face lah. But in that case where you pull your friend, walao, hit you in the face, very pain there. I feel the pain. Okay, so a chest expander works this way. There is forces. So whenever we think about forces, we should label them. So his hand will exert a force in this direction, pull. I didn't crop the hand, but another force in this direction pull. We need forces in both directions to pull the spring. So same thing, our boy here pull with force F. The other our boy here pulls with force F. So like discipline teacher. Boy, come here. Okay, so anyway, here each spring has an unstretched length of 0.63 meter. So you haven't stretched yet. This is the original length right here. Original length. I'm going to call this L0 or L1. Okay, but one important information here is this chest expander consists of 5 identical springs. So, I mean, here there are 3 elastic cords or elastic bands, but instead of this, we put spring. Okay, same idea. Parallel between 2 handles, so like this one. 2 athletes are stretching the chest expander by pulling 2 handles in the opposite direction. The spring obeys Hooke's law. Let us recall what Hooke's law is. Hooke's law is that law that tells you if you apply more force, the length will be longer. Remember, we did the experiment, we plot the graph. I'll explain what is meant by this statement. Okay, so there are 2 points that you can talk about when it comes to Hooke's law. Okay, so one thing, okay, so it depends on your brain. I want to help you hack your brain, but you need to identify which one is your brain. Now for me, because my brain likes equation, for some reason, it's just made that way. So when I see Hooke's law, I think equation, F equal Kx. That's me lah. Maybe it's my Chinese school upbringing. Which one is you? Let me know. Are you the type that you think about equation? Or you can say F is proportional to X. Maybe some of you will be thinking about graph. Oh, teacher, I remember, we plot the graph, or then we change the force here, and then we got different extension, extra length, and then we draw this graph like that one. Maybe some of you is so visual that you're actually imagining this person here stretching and compressing. You want to feel the force. You want to feel yourself doing this. Okay. To help your brain, it's better to remember all 3, to know all 3, to have access to all 3. Because it's a bit like I got three things to use, but I only stick to one. But you always have a preference one. So if you know how your brain works, like for example, mine is a lot on equation, then you can just start with the equation and try to write what it means by Hooke's law. Okay, so in Hooke's law, you can say that the larger the force, the greater the extension. Right? That is one of the key understanding of Hooke's law. And also, you can also talk about the proportionality relationship, this directly proportional part. So if you double the force, you double the extension. So I would say that first one, the extension or the increase in length, you don't want to use extension, you can use increase in length of a material. In this case, it will be the spring, is directly proportional to the force or the load acting on the spring. Okay, so the marks, right? 2 marks. 1 mark is when you mention extension directly proportional to force. This is 1 mark. 2nd mark is when if you talk about extension and you just talk about force, but you never mention directly proportional. You say something like, oh, the larger the force, the larger the extension. Or if I double the force, I double the extension. This part is 1. Very good one, like bonus. Okay. Next, each athlete pulls the handle towards himself with a force of 1003. So this is my F. calculate the tension in each spring. So this F4, the F here, 1300, they share the force across the 5 springs in between. So you pull 1300 here. This one is shared with 5 springs. So because it's shared with 5 springs, if I want to find each spring, I will take 1300 divided by 5. Okay, because we are putting them side by side, you stretch. All right. In fact, the more spring you add, the harder it is to stretch because the tension will be evenly shared. This 5 here shows that it is shared with 5 springs. Okay, so this will get you 260 Newton. No, you write unit. Okay, chest expander stretches and each spring.
Teacher.
Yes.
But the question 2, they say each athlete, so need to times 2 or no need?
Oh, good question. Do we need to times 2 or don't need? So here, if let's say I assume this athlete is not here, do you think can extend the spring? You one person pull with one hand.
No.
On one side. No. What will happen? The spring will accelerate towards you. So in order for this to happen, you need actually 2 forces, but we only take the value of 1 force. And then you may be thinking, but teacher, you know the pure picture or there, the normal one where I hang the spring here with the load like that one, the 最 normal one. This one got 1 force only. Actually, there are 2 forces. There is the spring pulling up the load. So this is force of the spring on the load. But then there's also the spring pulling the ceiling. And these 2 forces are the same. So it's actually 2 forces, but we only take 1 because it's not possible for you to extend any object if you only have 1. So that's why if you look at this statement, sometimes we say load acting on the spring is legit this load. So we only take this one. But it's a very good question. Constant confusion. So we take 1 only. Use F on one side of the spring only for all cases, including the original setup. So if you imagine if let's say I replace the ceiling with your hand will feel this downward force pulling you down. So it's these 2 forces that causes the thing to extend or compress. Okay. So divide by 5. No need to times 2. And you will see this again and again. They will try to confuse you. So number 2, we have this new extension. So this final length. And you're asked to calculate the spring constant. So you could think about the equation F is equal to Kx. And the force that we apply on one spring, because each spring has the same extension. Is tension same as force? Yes, tension is a type of force. A type of force on springs, normally we can label it anything. The symbol, okay, I'm going to write the symbol in red. Symbol can be T, can be F. Okay, on springs or string. Maybe the string is elastic, right? Right? So it's not tension. So on one single chord, this is 260. You want to find K. The extension is 0.94 final length. Need to minus the initial length. So scroll back up and find the initial length, 0.63. Then you can find the spring constant K. When you press your calculator, this one is 840. Unit left, teacher. Well, this 260 is Newton. So here will be Newton. Okay, 你拿过来除 bring here and divide. This unit was meter. Bring over and divide, so it's Newton, divide by meter. So Newton over meter. This means if I want to extend the spring by 1 meter, I need to apply 840 Newton. So to extend a single spring, although 1 meter is very long, 840 Newton is needed. This is what this number means. Newton per meter. Okay. Part 3, state the energy changes that take place as the two athletes use their muscles to stretch the chest expander. Of course, this one is, I haven't touched energy in our syllabus yet, but this is basic energy conversion. What energy is stored inside the body of a human being? You eat food, so you got gains, you can build muscle. What energy is there? What is the energy? You eat food, then your body take that food.
Chemical.
Yes, correct lah. Chemical energy. Your, mitochondria inside your cell, right? Mitochondria, it take the oxygen, it take the glucose from your food, and then they do some chemistry and then create ATP energy. I'm a physics teacher. I don't remember the process or the cycle, but that's the idea. Our body can convert sugar and fat and protein if needed, but fat and protein will still become sugar one. And then that is your chemical energy. So our friend here, our athletes here will have chemical energy to, I guess you stretch the spring, so it's elastic potential energy. IG very easy one. You mention chemical energy, you get 1 mark L. You mention 2 elastic potential energy, you get 2nd mark L. This one, you write F equal Kx, you get 1 mark L. You show substitution, and then the final answer, you get 1 mark. It's very nice. Okay, so mark your own work. Try and see whether got any mistake or not, make some correction. Then we'll move on to some of the pressure question. Then I will talk about what modification we need to do when it comes to pressure in water, liquid. Okay, not water, can be oil, can be alcohol. Okay, so this pressure is defined as force per unit area. This is the general definition. Okay, any kind of general format can fall back to this one. Okay, so the pressure is, we studied different example on how to increase or decrease the pressure. So application of high pressure is either we make the force very big or we make the area very small. So example, knife, edge, your football boots. And we want high pressure so that there's more grip or we can cut our carrot. Okay, and sometimes we want low pressure. So we make low pressure by either small force or increase the surface area. So example of this would be snowshoes, although you technically will never wear it in Malaysia, where the base is very wide. We also learned that people change tires in the snow, they use a wider tire or large tires, especially the construction site ones. Okay, so here is a few examples of us looking at pressure in the solid format. So for solid, it's very straightforward one. What causes the force? For solid, it's easiest to see that this is your mg, your weight. And then the area for solid is also very easy to tell. This area is 90 degrees to weight. Make sense, ba? So right now you have these concrete blocks, and these concrete blocks, let's say I assume that it's a uniform block. So the weight is right in the middle like this, this is mg. So this one is also the same law. This weight push down, this weight push down, this weight push down. So I can just mg the whole thing. Okay. So when it comes to force, because the weight of this the same concrete block, they should have the same weight. So the force of stack A on the ground is the same as the force of stack B on the ground. The same. Because they are the same blocks. Okay. Now, which pressure is higher? So the pressure on the ground from stack B, if you look at B, the area for B that is in contact with the ground. Let me draw for you. This area, teeny tiny area here. This area is so small compared to the area of stack A. I think instinctively also you know this. You want to carry dictionary. You carry, which one you carry? How will you carry a dictionary? Of course, A lah. How can you going to stack your dictionary like that and carry? What is dictionary, teacher? I use Google. Google can. Sure. So this area is a larger area. So pressure on the ground from stack B would be greater than the pressure from stack A because the area in contact with the ground for B is less than for A. Right? So in this case, we are using different area. Small area, high pressure. Large area, low pressure, because the force is the same. All right. Same as C. The weight is 500 Newton. Area in contact is this much. Calculate the pressure in Newton per cm squared. So this is just using the equation. Pressure is force per unit area. So you take 500 by 200. You will get 10 over 4. 10 over 4. 0 0.25. 250. 10 over 2.5 Newton per cm cube. Cm squared, sorry. All right, next. The figure shows a tire. This is the second question. Figure shows a tire acting on a large earth-moving vehicle. When the vehicle is loaded, the area of each tire in contact with the ground is a rectangle of sides 1 meter and 0.5 meter. So right now we assume, it's a close enough assumption, that this is the part that is in contact with the ground and it's the shape of a rectangle like this. This is my rectangle. Okay. So you imagine, if let's say you do any rolling, you will notice that the shape that they make is actually a long rectangles as the wheel rolls around. Okay. Calculate the area in meter square. Area is 1.0 times 0.5. 0.5 meters square. Great. You write two significant figure, okay? Because this is two significant figure. This is two significant figure. So this one should be two significant figure. You learn significant figures already or not? In maths. Yep. So in physics, we calculate, we care about significant figures. So this is the difference with SPM. SPM will tell you can decimal point. Okay, but the actual right way to look at it is significant figure. If I measure things, I can measure to two significant figure, then my final answer can write two significant figure. But SPM, they follow decimal point. So please just verify with the syllabus. Okay. So in part 2, the vehicle have 4 of these tires. Okay. Standard vehicle. Calculate the total area. Wow. Okay, sure. Total area is 4 times 0.50, which is 2.0 meters squared. Sure. The vehicle is loaded. Calculate the pressure in Newton per meter square. All right. So The weight is 10,000, so pressure is force over area. 100,000 divided by, where is meters? 2.0. So this will be 50,000 Newton per meter square. Large pressure. All right, and finally, I started to introduce some water into the equation. Okay, so a rectangular storage tank with the base, I draw all the dimension for you already. Okay, it's filled with water of a depth 2 meters. So I just fill in the whole thing with water. Or fill in the whole water from the base to the, basically the whole thing lah. Just fill it in with water. Okay, calculate the volume of the water in the tank. This one is a no-brainer. 3 times 2 times 2, which is 12 meters square. Calculate the mass of the water. Well, we have the density. So for B, density is mass over volume. So mass is density times volume. Okay, this symbol is pronounced as rho. I will show you how it looks like in Greek format. Actually, I have a Greek keyboard. I just don't remember. Correct lah. This is my Greek keyboard. Rho. This is rho. Okay, you know why I write my rho this way? Does it look like a symbol? You want to guess why? Because if I don't write it this way, you know what will happen? 我写下 I write, then it will look like P. Doesn't it look like P to you? It looks like P to me. So I have pressure, which is P, and I have density, which is rho. And if they look the same, GG lor. Eating cancer, square, some weird thing will happen, and then I wrong. So I write like that. I tend to write my density this way because of this, but your teachers may write this way. Looks a lot like P there. Even if they write like that, it looks like P. After they write a bit, then it looks like E. So I write like that. Just 讲一声 first, in case you see this and your teacher write a different symbol. What I would suggest you write, follow me. Yeah. Okay, so rho is a symbol for density. It's also a symbol for other stuff, but if we encounter them, I will let you know. Okay, let's continue. Density is 1,000, volume is 12. Meter, so all is good. So this is 12,000 kg. Okay. Calculate the weight of the water. Well, weight, let me put W is equal to mg. So 120,000 times 10. 120,000. All right, D. Calculate the pressure at the bottom of the tank. Teacher, water also can use pressure is force per unit area. Can we assume that the center of gravity of the water is still acting down like this, unless water's gravity act differently. Cannot be right. Gravity pulls everything down. So this is your W. So this F is equal to W. We're going to put that in. 120,000 divided by, what's the area? Oh, 12. 12? I know, sorry, paiseh. The area is this one. This is the area, right? Oh, okay. This is area. Let me change color. This is A. So A is 2 times 3. Beautiful. So divide by 6. 20,000. Okay, 12 divided by 6 is 2. Unit will be Newton per meter square. Or if you're feeling fancy, you can put Pascal, PA. PA is for Pascal. All right. Are you ready? It's time for big brain. So I'm gonna just look at this and I go like, well, 好像很烦呢. I need to go through so many process. I need to find the volume. So I can find the mass. So I can find the weight. So I can find the force. So that I can find the pressure. Okay. So from volume to mass to weight to pressure. Teacher, very tired. Got shortcut. Got. I show you the shortcut. So the part of this, right, is that to notice whatever thing that you repeat 2 times, which is this 2 times 3. You see here, 3 times 2. If you repeat the 3, if you see and you multiply 3 times 2 here, then you divide by 3 times 2 here, this means you actually don't have to use 3 times 2 one. But you need to legitimately come out with an equation so that if you don't divide by 3 times 2, you won't gonna GG by your own teachers lah. All right. So right now I'm going to talk about how to do that, especially for water pressure. And to do that, I'm going to copy the same picture again. I want to crop it. So that'll be a new page. Hopefully you copy already. Okay, let me know. All right, so this is our good old water tank. I'm not going to draw out the water anymore. But instead of 3, 2, and H, I'm going to just change. Okay, light. Maybe this one I call H, height. Can? Maybe this one I call X. Maybe this one I call Y. Doesn't matter lah. I think this one's Y. So ugly. BRB. So we learn algebra for this very purpose. Is there a faster way? Because these steps feels very CN. So I'm gonna delete the whole thing. Okay. So I let this one be X lah. This one be Y lah. And this one be H. Height. Doesn't matter one. Put your favorite alphabet. If your name is Jordan, you can put JR. Matthew can put MT. All right, so what was our process again? We know that the pressure on the bottom face, which I'm now going to just roughly highlight as yellow, the pressure on this bottom face is due to the weight of the water. The weight of the water pressing down, this is mg. So I'll start off from the back. Previously, we did, okay, I'm going to draw here. We did volume to weight to pressure. I will reverse the process because I want to see if there's an equation that I can use. So I will start with pressure. Pressure is force per unit area. So if I want to find the pressure of anything at this level on the bottom face, let's say I put this to squish, I don't know lah, my tofu or whatever I'm squishing. So I want to apply pressure on this point. This F is actually equal to my mg. Hello, so I put it right? Pressure is force. Force is mg over area. Now, before you kanchong spider, think about how we introduce density. Because look, I can put water in any container I want. Can be rectangle, can be square, spherical, what sort of funny shape, pyramid, also can. But I can never change the density of water. So I'm thinking to myself, maybe if I put density in, I got one last thing to calculate because density of water is always the same. So from density, rho is equal to mass per unit volume. I can actually find mass, which is density times volume, which is what we did just now, right? Remember? So here I'm going to take density times volume times G divide by A. Now, before you panic some more, volume of the cuboid, area of the yellow color rectangle. If I take and divide, will I get H? What do you mean? Well, you see, volume B, use different color for this. Volume is equal to XYH, right? So this one will be density G. Put what you want to put here? XYH. And what is area again? Teacher, area is XY. Oh, correct. No? Area is XY. Oh, the XY can cancel. The 3 times 2, remember? You times 3 times 2, you divide 3 times 2, might as well don't do anything. So the XY and XY2 bye-bye lah. I show you working again. Normally I can point on the other side of the board, but I don't have the other side of the board for you. So ta-da! 3 times 2 here, divide 3 times 2. So basically all this process that we are doing, we are trying to use algebra to help make our life a bit easier by doing something a bit difficult now. So the XY and XY can cancel. And what equation do I have left? Wow, I have rho HG. Draw a square rectangle. Ta-da! So this is pressure of liquid. So you may be asking, teacher, can use for all liquid? Yes. Any shape? Yes. As long as you know the depth. This H here. H is the depth of the liquid. Sphere's height is the diameter, correct? How deep is the liquid? How deep are we talking about? So from the top of the surface of the liquid to the bottom. Rho here is the density of the liquid. And G is 10, your gravitational acceleration. Gravitational acceleration. 10 Newton per meter squared. Why is there a G there? Because the force is M times G. Like we did just now, the calculation. That's why I included that example. Because it's the same equation. So this equation is a fine-tuned one, an optimized one, so to speak, or a shortcut one from force per unit area. Let me put here so the whole thing is on the board. From force per unit area, we came up with this equation. Are they two different equations? No. It's the same equation. It's just that instead of going through the multi-step process of finding the mass and then find the density and then find the force and then find the pressure, I can just fast forward and just multiply by density and height, the depth of the liquid. Okay. Before I carry on, let me show you some visual things. Ask questions, by the way. I expect some hesitancy one. Ask. If God, you ask. Let me load the simulation for you. Any questions? If not, I ask you a question now. I regret. I should have asked a question. Yeah, I should have asked a question. Hang on. Let me ask you something. What if I flip this? Make it. I flip like that. Can I still use the same equation, teacher? Remember I said anything goes? So of course you can. But teacher, the area or change leh. Doesn't matter. You just label your HXY differently. This one now become your H. Okay. And this area will be your new area because where does weight act on? Weight will act on this part here. Pull. This is mg. 90 degree to this area. So this one is x law and one is y. So when you flip it, everything, the derivation is the same. I just changed the labeling canon. Because whenever you use force per unit area, it has to be the force divided by the area that is perpendicular to the force. All right. So this is fluid. Oh, my keyboard still in Greek. Paise. Hang on. You can add that as your custom keyboard one. Why hello, excuse. Oh, it is small. Fluid pressure. Okay, time to play with some simulation. First one. All right, look at our diver here. You can move him up and down now. You can see the equation, the pressure equation. Well, I hope it's big enough. Okay. The pressure equation here is rho GH. So there are a few things that I can adjust. This diver is in the deep reservoir. Okay lah, he's about to dive. So at this point, the water pressure on him is 0 because he's on the surface of the water and there's nothing pressing down on him. Weight is 0. Pressure 0 lor, because the height is 0. But acceleration of gravity is still 10. G is still 10. And the density, of course, this density we can adjust. This is just normal water. Pure water is 1000. But maybe this one got impurity there, random fish swimming here and there, poop inside the water, density increase a bit low. Okay, let me decrease it to 1000. So the number nicer. Okay. Now we're going to put him to go sinking. Okay, let's sink. Let's say he 潜水. Okay, at 4.48. You notice that his pressure increases. Makes sense, right? Because now you have this layer, this top layer of water pressing down on him. Does the shape of the reservoir matter? Let's see. You keep your eye on this 44834. I go and change the shape. Okay, reservoir is very narrow. Did this change? No. But teacher, the area not smaller, man. Well, the area of the reservoir is smaller, but the area of his body is the same because we are looking at the pressure on the human being. So the human being surface area is the same. I mean, it's not like he dive inside and he inflate, right? That'll be very disturbing. You go diving and then you inflate to double your size. I stress. You are not a sponge, okay? You don't absorb water, so you will not inflate. So the area of the man is the same. In fact, he can turn around, do somersault, take picture, starfish, selfie, all that can. Pressure the same. Because liquid pressure only depends for the same object. Actually, no. Just liquid pressure only depends on the height. This one don't change one. Gravity never change one. So it doesn't matter. Put big reservoir, small reservoir, pressure the same. The only thing that will change the pressure is if I move this one down, deeper, or high. Second observation. You notice how this part is thicker. This part is thicker. Because when you build reservoir, show you real life water reservoir. If you got watched show before, in the real life water reservoir, it looks like this. You see? Here down, always thick one. I mean, this one is like very nice, but now I feel like going up. You see here, this part here is thicker because the water pressure underneath is very high. So we need thicker concrete so that it doesn't crack. Okay, so this simulation hopefully helps you understand. You can swim anywhere. So if I maintain the same height, it can be anywhere of the water as long as the height is the same, the pressure is the same. Can even be here at around 5 meters. All cool, no problem. Of course, if I increase the water level, then the pressure increases. All right. Okay, so that's the first observation. Pressure only depends on height. Pressure in liquid only depend on H. Different H, different pressure. Will the pressure change if the guy's volume changes? No. Because you see, if his volume change, this number on top is bigger. But also his area is bigger. So they cancel out. Does that make sense? When your volume increase at the same height, so surface area, the area increase, then the volume also increase. So 上面下面 cancel 了, not important. Because if you are bigger and you have more area, you also experience more force. There's more water on you, so they cancel out. All right. So only depends on height, not shape, not volume. Okay. In liquid of the same density, of course. If you have liquid of different density, then it's a different story lah. All right. Okay. So let me adjust pictures a bit so I can crop the picture for you. So if we look at our hydro dams, so nice, this hydro dam. Malaysia also got one, but got a few actually. I think got one is Langor one, where the water got problem, then we don't have water last year or something. So this part here, the water is thick. I want to draw it here. So normally when we build a reservoir, it will look like this one. If I cut, I cross section it, okay, and the water is here. So I fill it in with water. Only depends on height. So as you go down, you travel down, your H increase. Let's say when you are here to here is your H. If you are here to here is your H. If you're right at the bottom, here to here is your H. So if you travel downwards, H increases, pressure increases. So this part here, you have thick walls to account for the increased pressure. So there's no crack. You spell properly. I just suggest thick walls, thick concrete walls. All right. That's the first thing that we can look at for liquid pressure. The second one that we may want to consider, simulation-wise, I'm going to put here. Later, I'll put it inside Google Classroom, the link, if you want to play with it. The other one would be this one. Too many windows. Okay, this one is quite fun, so I'll send it to everyone in the chat. But I also know if you're working with one screen, you cannot look at many things at one time, okay? All right, so I'm going to use metric, okay? Not some weird unit I don't want for now. So let's see. I can take this. Okay, let me refresh for you. When you open, it looks like that. Okay, so as usual, we can adjust the density, can put gasoline, which is petrol. It's American English for the word petrol. Okay, or we can put honey. Never mind, let's stick to water. Okay, gravity is Earth. The correct value is actually 9.8, but normally we approximate to 10 now, okay? And now, I guess if you want, you can put a ruler here just to measure the height. And then I'm going to include some grids so that it's easier for me to measure the height. Okay, so right now I will open the water and I'll just let everything flow to maximum. Okay, then I put my meter here. I want to measure the pressure at the bottom. So this one is by calculation. If you multiply all the values, you get this kilopascal. So 1000 times, I mean, it's not exactly at 5, but it's close enough. Anyway, somewhere here. So it's not the absolute value. Look at the trend. Right now, if I remove water, you will see the pressure will drop. You see now, pressure dropping. So eventually, if I remove all the water, you get this number. This pressure is where one is from atmosphere. Atmosphere got pressure pressing down. So I will reserve atmosphere for next week because we want to bring in atmosphere, then we got problem. Not problem now, we need to do extra consideration. So I'm going to turn off the atmosphere and assume this is in vacuum. So outside pressure is here. Fill this in with water again. Okay, put this one here. So now you notice that this is around 30, which makes sense because the depth is, the depth here is 3 meters. So 3 times 1000 times 10 is around 30 kilo. Okay. And then if I remove the water, it will drop eventually to 0. If I on the atmosphere, what will happen is you will notice the atmospheric pressure is actually quite high. 103. So, right, an interesting fact about this that I probably will re-emphasize next week is that our bones, our body is used to 1 atmosphere, is used to so much force per Newton, for so much Newton per meter square on your body. So if you go to outer space into vacuum, you will explode. Your body just don't know how to deal with 0 pressure. Okay, let's change shape. I wonder if the pressure is the same. Down here, 117,864. Down here, still 117,864. Same height, same pressure. I put it at 2 meters. Can I just put it exactly at 2 meters? You can play with it, okay? So if you don't want the atmosphere to kakachao you, then you turn off the atmosphere. So the shape doesn't matter. What about this one? Did I put it here? It's okay. This one is something else. But yeah, the pressure is only dependent on height. If let's say I keep the height the same, so I try to keep this at the same height, it will have the same pressure. Okay, go and play with it if you want to. But that is the whole idea of fluid pressure, only dependent on height. Okay, so next we are going to look at this thing called the hydraulic jack. So I'm going to steal one from your textbooks. I have it here. Correct. So if you go back to your textbook, I've already covered all of this. Okay, so examples of this is number one, you can see at different depth, you have different pressure. Okay, so pressure increases with depth. Here, number one. Pressure depends on the density as well. Two. But pressure doesn't depend on the shape. So P is equal to H rho Hg. All right. One more thing that I didn't mention is that pressure acts in all directions. So if I go back to that simulation here, it doesn't matter whether I put the thing here or here. I expect the same pressure acting equally in all directions because of the random Brownian motion of the particles. Okay, so in this case, you can see that the pressure will increase with depth, but the pressure also act in all directions. So when you water stuff, you know that the water will shoot out this way. Pretty standard stuff. Okay, so yeah. And in this case, right, sometimes when we go deep into ocean, any kind of deep sea diving vessel has to withstand the high pressure of water pushing in on all directions. You have water pressure going in, pushing in all directions. The value is the same for the same height, but it is compressing it in all directions. If you have a hull breach, then it's likely that everyone will die. So it's highly unlikely that you can survive. It's a bit like if you have a hull breach, basically if there's a break in the system for an airplane, humans are not supposed to fly so high or go so deep one. So our body cannot deal with high pressure. Our body cannot deal with low pressure. If we are forced to deal with it, we'll probably die because we are just biological beings. You know, the cabin will pressurize, right? When the aeroplane fly, you can feel the pressure changes in your ear. That's because they're trying to adjust the pressure so your body are used to it. Okay, so anyway, let's carry on. We have done the equation. I have derived this H rho G here. This is the derivation. They use a cube because cube is easier. Okay, so this part is okay, no problem. So when it comes to hydraulic system, right? Okay, this is where we can use the transmission or play with this equation. P is equal to F over A. Okay, to adjust things. So for example, if I want to carry something heavy, but I don't have strength or muscle, like for example, I want to stop a car, but you know, I'm a human being. I can't stop a car. So what I would do is I would transfer the force from my feet to the braking system or the brake pad of the car. Okay, let's read first. Okay, in some machines, the forces are transmitted by liquid under pressure. Machines like this are called hydraulics. Okay, this is what we'll do next week. Okay, but the hydraulics make use of two things. Number one, liquid cannot be compressed. Okay, number two, pressure in the liquid is transmitted to all parts of the liquid. So everybody gets the same pressure. So if you go back to this simulation, just as an introduction, and if you look at this hydraulic part, you see there's a piston here. Let's say, put this one here. Can I put it here? Hello, excuse. Okay, and it compresses the liquid. You can see, right? It's compressing the liquid. But do you see this water level rising? Okay, maybe I should let go now. You see this water level rising. So let's say I look at this part about 3.88 and I add, you can see the pressure increasing, right? I add because the water level is rising. Okay. Then I add some more. Okay, so if let's say the pressure is increasing and the water is being pushed upwards, I can actually support another weight here. Or in other words, when I draw the system out like this, it will be something that looks this way. Let's say you press down. So imagine this is your hand, you press down on something. Okay, this is the input of force. It acts on the liquid. It can be oil. Normally in car, we call it braking fluid. Okay, so when you press down, the pressure is transmitted all the way, and then the object will be lifted up. Okay, so I think I should show you some real life scenarios, and then we can call it a day. This will not come out next week. Okay, next week we will stop at P equal to F over A and the H rho G calculation, not hydraulic jack. Okay, so for here, when the piston you press down, the force or the pressure will transfer all the way to here. It's a bit like this one lah, my dudes. When I add this one here, the force and pressure is transferred to this thing. So when I press down, this one will actually go up, actually by the same amount. Okay, so I've seen one. Normally I can build this in the lab for you to experience, but what is lab online now is a bunch of simulations. Okay, this one. I see so many ads by this person there. I guess he's very productive for. Okay, hydraulic pressure. Okay, so what we have here, as usual, is some slotted mass. You notice all the simulation will look the same because we are demonstrating the same thing. So we have slotted mass here. And then inside here, we will put some incompressible fluid and it's linked together. Cannot really tell, but hopefully you can see. And then we can see that as we transfer, hopefully as he transfers, the weight from one side to the other side, to reach a point where the force is transferred, then the liquid will go. So force is transferred from one arm to the other arm. Connected, I mean, it's connected lah. Here to here is connected one. Okay, so if we change the mass and we measure the area, notice this is the narrower area, this is the larger area. There's an equation here that relates force and area because the pressure have to be the same, right? So if let's say you think about the hydraulic jack, I'm going to go back to this picture and just tell you what the idea is. Here you have small area. So here you have small force. Because you use your hand and punch, right? One punch, you one punch the thing here. Small force, small area, and then you have pressure. This pressure here is evenly distributed and transmitted to this object being lifted. But this object being lifted is heavy. See this 120 Newton compared to this 12 Newton. Here you have large force needed to support a heavier weight. Okay, and then here would be large area. So the pressure here and the pressure here is the same pressure. So I can say because the pressure and across the whole system is the same, that the force, okay, I don't like this equation. I like the equation of Force over area of this side, let's say I call this input lah, or IN, or I1, I guess. Small f1, small a1 is equal to f2, a2, large f2, large a2. Because why? P1 is equal to P2. So the pressure is equally transmitted. So later when you help your mother, I guess, water the plants, you can see Pascal principle happening. Okay, but yeah, that's it. We also use this to brake, B-R-A-K-E, brake the car, because here your feet, small force, put on a piston with small area, transmitted to brake pad, larger area. So here we'll have a larger force. Did you create more force? No, 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 you didn't. It's the same. You didn't make your own energy. You didn't create your energy. It's the pressure that is being transferred from one point to another. Okay, so hang on to this idea first. Okay, walk around. I will go and find a nice one that, because I found some that I cannot find right now of someone using a hydraulic jack to lift up a sofa. That one is very cool. I like that. The one he built himself on. Okay, so what do we learn today? The main idea here is to understand that pressure in liquids can be calculated using the equation. P is equal to FA. But if I use the equation P equal to FA, normally 很麻烦. So we prefer to use the equation P is equal to H rho G, or rho Hg, but they are the same equation. Okay, this is the true for this one. 下一代. Okay, so the next thing that you should know is, number one, pressure acts in all directions. This is actually your Pascal principle, got name one. Okay. Number two, pressure increases with depth and pressure depends on the density from the equation. And pressure doesn't depend on the shape of the container. So as long as you are the same depth, you look at the arrow, same depth, you will have the same pressure. Less depth, you have less pressure. Okay. And we're going to apply the idea that pressure acts in all directions to your hydraulic system next week after the test. But focus on what is going to come on your test. We're going to stop the test at this page. Here. Basic stuff. Okay. Can. Alright, that's it. You want, you can play with the pressure thing. I will put up some links on Google Classroom by the end of the week, this weekend. So either today or tomorrow lah. I'll stop recording now, but don't go first. I need to screenshot the 10